Probably the most complex component in this model is the connection between the clamp and the load, and furthermore the method for switching this connection on and off. Let me first start, and almost naturally, but you could expect it, by saying that there is several methods for connecting the clamp and the load. One way would be like a mathematical approach. You can actually create a lock joint between the clamp and the load, and you can actually switch this joint off, not directly in one run, but using several simulation runs. And the trigger point for the switching of that joint can then be determined by defining a sensor. A sensor being an object in Atoms that can stop the simulation. So you can actually say, okay, I want to stop the simulation when a certain point has been passed, and after I have stopped the simulation I want to switch off a certain joint and continue simulating. Again, this would be a mathematical approach in creating the connection between the clamp and the load and switching it off. A second approach could be to realize that this clamp is like a magnet, and this magnet will have a physical size same as the load. So you can actually say, well, let's make a contact between the clamp and the load, prohibiting the load to pass through the clamp, and then let's additionally create a force between the clamp and the load, pulling the load into the clamp. So with that you've actually defined the magnetic force keeping the load onto the clamp, and this force can be triggered off, can be switched off at the point where you want to drop the load. So that would be method number 2 to create the connection. In this example we have used a third method. That's like, well, maybe representing a hand from the clamp grasping onto the load. This hand can be modeled using one of the force elements, and the most generic way for doing that is using a G-force. Let me just show you how you can start doing that. You create a G-force between the load and the clamp. You define the position where to set this force, and now you can have a look at the components in the force. Don't get confused now, but basically this is nothing more and less than 6 linear spring damper forces connecting the 3 directions and 3 rotations relative between the 2 end parts. So basically what you have here is the equations to define these 6 springs and dampers. If you would now be able to switch those forces off, switch those springs off, you would be able to really grasp an object and then releasing it at a certain desired point. And this is actually been illustrated in this example here. So here we have this force vector F clamp. It's not 6 components but only 3 for the longitudinal components. The components of this force represented by the following equations. I have cleaned up the equations a bit, but basically what it says here is that the force in x direction is equal to a switch, something like an on and off switch, multiplied by a stiffness, multiplied by the deformation, multiplied by damping and damping velocity. So this switch clamp is the main trick. If we make that a variable with value 0, then the spring damper force will be 0 and the object will be released. Directly from this info panel we can actually check what the behavior of this switch clamp is. We can click on the object, click on apply, click on modify, open up the function builder and see indeed that this is a step function. It is still simply modified as a function of time, but we might as well have introduced here a position or a relative position triggering the switch to be set off. If we plot the variable right now, we see that indeed it switches over from a value 1 to a value 0 between 21 seconds and 21.1. So this is a quite abrupt switch off of all 3 forces to drop the load into the bucket.